Somewhere in our galaxy right now, there is an object that no one can agree on. It glows faintly, not with reflected light like a planet, but with its own dim heat, radiating into the cold of space. Its surface temperature sits at over 1,000 degrees Celsius. It has never ignited, never fused hydrogen in its core, the way a true star does, yet it burns with a quiet, stubborn warmth that has lasted for billions of years. Its mass sits at roughly 12 times that of Jupiter, teetering right at the edge of a threshold that separates worlds from failed stars. So here is the question that is quietly unsettling some of the brightest minds in astrophysics right now. What exactly is it? Is it a planet, an extraordinarily massive one, pushed to the absolute limit of what we allow that word to mean? Or is it something else entirely? A star that almost happened. A sun that ran out of fuel before it ever truly burned. As of early 2026, NASA has confirmed the existence of more than 5,500 exoplanets. But buried within that number is a growing population of objects that refuse to behave the way planets are supposed to. They are too hot, too massive, too energetic, and yet not quite enough of any of those things to cross into the category we reserve for stars. Scientists have a name for the boundary where this confusion lives. They call it the brown dwarf desert, a strange or almost empty zone in the cosmic population chart, where almost nothing seems to exist, and the few things that do exist make our current classification systems look embarrassingly incomplete. This is not a minor technical debate happening in the footnotes of academic journals. The question of where a planet ends and a failed star begins cuts directly to how we understand the formation of solar systems, the conditions that allow life to emerge, and ultimately, what kind of universe we actually live in. If you want to follow that question all the way to the edge, subscribe. But right now, let us begin. To understand why certain exoplanets look more like failed stars than worlds, we first need to understand the boundaries that science has drawn, and more important, why those boundaries are far less solid than they appear. Let us start with the numbers, because in astrophysics, mass is everything. A true star sustains itself through nuclear fusion in its core, specifically the fusion of hydrogen into helium. For that process to ignite and sustain itself, an object needs to reach at least roughly 8% of the mass of our Sun. Below that threshold, the gravitational pressure simply cannot generate the temperature and density required to keep hydrogen burning. The object collapses partially, heats up slightly, and then just sits there, cooling, slowly, for billions of years. That is the upper boundary. Now consider the lower one. Scientists currently place the dividing line between a massive planet and a brown dwarf at approximately 13 times the mass of Jupiter. At that threshold, something interesting happens. The object becomes massive enough to fuse a heavier isotope of hydrogen called deuterium. It is not the sustained luminous burning of a true star. It is more like a spark that flares briefly and then fades. But it happens. And for a long time, that was considered enough of a physical distinction to justify drawing a line there. So the picture, on paper, looks clean. Below 13 Jupiter masses, you have a planet. Between 13 and roughly 80 Jupiter masses, you have a brown dwarf, a failed star. Above 80 Jupiter masses, nuclear fusion takes hold and you have a true star. Here is the problem. Think of it like a campfire. A roaring fire is unmistakably a fire. Cold, wet wood is unmistakably not. But what about wood that is slightly damp? Wood that catches briefly, smolders, produces heat, and then dies out before anyone agrees whether it was truly burning. That middle condition is not a clean category. It is a process. And the universe produces an enormous amount of objects that are caught somewhere in that process. The deeper problem is our instruments. The transit method and the radial velocity method, the two techniques responsible for discovering the vast majority of known exoplanets, tell us an object's mass and radius. They do not tell us how that object formed. And formation history, as we will see, may be the only thing that truly separates a planet from a failed star. Scientists call this the minimum mass degeneracy problem. Two objects with identical masses can have completely different origins, one built slowly from a spinning disk of gas and dust around a young star, the other collapsing directly from a cloud of gas the way stars do. Same result on paper, completely different story underneath. The universe, it turns out, did not consult our textbooks before deciding how to arrange itself. Theory is one thing, but the universe has a habit of making arguments concrete. So let us look at 4 specific objects that sit at the center of this debate. 4 cases where the data itself forces us to ask whether we are looking at a planet or something that was never quite supposed to be. 1. Case 1. Kelt 9b, a planet hotter than most stars. Kelt 9b orbits its parent star at a distance roughly 10 times closer than Mercury orbits our Sun. Its dayside temperature has been measured at approximately 4,300 degrees Celsius. To put that in perspective, that is hotter than the surface of most red dwarf stars, the most common type of star in the entire galaxy. Its hydrogen atmosphere is not stable. It is actively being stripped away by the radiation from its host star at an estimated rate of 100,000 tons per second. Every second that passes, Kelt 9b loses material equivalent to a small mountain. What makes this case scientifically significant is not just the temperature, it is the behavior. Kelt 9b is dying in a way that mirrors what happens to stellar objects under extreme radiation pressure, not in the way we would expect a planet to age. The data here is confirmed. The interpretation that this object occupies a behavioral category closer to a stellar remnant than a conventional world remains an active area of analysis, not settled science. Case 2. Brown dwarfs with planetary atmospheres. Since the James Webb Space Telescope became fully operational in 2022, observations have returned something unexpected. Several isolated brown dwarfs, objects with no star to orbit, drifting alone through interstellar space, have shown atmospheric compositions containing water vapor, methane, and carbon dioxide in ratios that look far more similar to the atmospheres of giant planets than to anything stellar. This matters because atmospheric chemistry is one of the few tools we have to infer formation history. If a brown dwarf formed the way stars form, through the direct gravitational collapse of a gas cloud, its atmosphere should reflect that. Instead, some of these objects are showing us chemistry that whispers of a different origin. Scientists are careful to note that these findings are recent and require further confirmation. But the pattern is emerging, and it is difficult to ignore. Case 3. ROXs 42BB and the distance problem. ROXs is a directly imaged object with a mass estimated at somewhere between 6 and 10 times that of Jupiter. It orbits its host star at a distance of approximately 140 astronomical units, roughly 140 times the distance between Earth and our Sun. Here is why that distance matters. At that separation, the standard model of planet formation simply does not work. Planets build themselves gradually from material in a protoplanetary disk, a spinning flat structure of gas and dust that surrounds a young star. But that disk does not extend nearly far enough to explain an object forming at 140 astronomical units. The numbers do not add up. The leading alternative hypothesis, and it is presented here explicitly as a hypothesis, is that ROXs formed the way stars form, through gravitational instability in a larger gas cloud, and then settled into what looks like a planetary orbit. If that is accurate, then calling it a planet is technically convenient, but scientifically misleading. Case 4. WD 1856b, the survivor. WD 1856b orbits a white dwarf, the cold, dense remnant left behind after a star exhausts its fuel and sheds its outer layers. The white dwarf it orbits is approximately the size of Earth. WD 1856b itself is estimated to be several times larger than its host star by volume. The puzzle here is not the size relationship, it is the survival. The region where WD 1856b currently orbits would have been completely engulfed during the red giant phase of its host star's life cycle. By every standard model we have, this planet should not exist in its current location. It should have been consumed. The current working hypothesis is that WD 1856b migrated inward after the red giant phase ended, pushed by gravitational interactions with other objects in the system, but that hypothesis has not been confirmed. What we can say with certainty is that this object witnessed the death of its star and remained. It is, in the most literal astronomical sense, a survivor of an event that should have erased it. 4 objects, 4 different ways the universe is quietly refusing to fit inside the categories we built for it. Here is where the debate stops being purely academic and starts revealing something uncomfortable about the state of modern astrophysics. We have 2 competing schools of thought, and they are not simply disagreeing about edge cases. They are disagreeing about something more fundamental, what the word planet is actually supposed to mean. The first school argues that classification should be based on formation history. A planet is an object that built itself gradually from the disk of gas and dust surrounding a young star. A brown dwarf is an object that collapsed directly from a gas cloud, the same way stars do, but without enough mass to sustain fusion. Under this framework, origin is identity. How something came to exist determines what it is. The second school argues that formation history is largely unobservable and therefore scientifically impractical as a classification tool. What we can measure, mass, temperature, atmospheric composition, orbital behavior, should define the category. Under this framework, what something is right now is what matters. Its past is irrelevant if we cannot verify it. Both positions are defensible. Both have serious scientific support. And they regularly produce opposite conclusions when applied to the same object. What makes this particularly striking is that the International Astronomical Union, the body responsible for official astronomical definitions, does not currently have a formally ratified definition for the word exoplanet. The definition of planet that generated significant public debate in 2006, the one that reclassified Pluto, applies only to objects within our own solar system. Beyond that boundary, the term exoplanet exists in a kind of definitional grey space. This means that when scientists report the discovery of a new exoplanet, they are using a word that has no universal legal scientific definition behind it. Consider that for a moment. We have confirmed the existence of thousands of worlds beyond our solar system, and we are still debating what to call them. The universe has been producing these objects for billions of years without waiting for us to agree on the paperwork. To be fair to the established framework, it deserves a genuine defense before we continue pulling at its seams. The 13 Jupiter mass threshold is not an arbitrary line drawn on a whiteboard during a slow afternoon at a research institution. It corresponds to a real physical event, the ignition of deuterium fusion. That process actually happens inside objects above that mass. It produces measurable energy output. It affects the object's thermal evolution over time. The boundary is not perfect, but it is grounded in observable physics, and that matters enormously in a field where speculation can outrun evidence very quickly. There is also a practical argument that rarely gets enough credit. Scientific classification systems exist not just to reflect nature accurately, but to allow researchers across different institutions, different countries, and different decades to compare their findings meaningfully. A shared vocabulary, even an imperfect one, is infrastructure. Dismantling it without a superior replacement does not advance science. It creates noise. And if we are being fully honest with the data, the majority of confirmed exoplanets behave exactly as the standard models predict. They follow expected orbital mechanics, display atmospheric properties consistent with their mass ranges, and fit comfortably within the existing classification structure. The edge cases we have been examining are genuinely unusual. They are not representative of the typical exoplanet population. But here is where history becomes relevant. In 1930, Pluto was discovered and immediately classified as the 9th planet of our solar system. That classification held for 76 years. It was not overturned because Pluto changed. It was overturned because our instruments improved, our surveys expanded, and we discovered that Pluto was simply one member of an enormous population of similar objects in the outer solar system that we had previously been unable to see. The classification was not wrong because someone made a careless mistake. It was wrong because the data available at the time was incomplete. That is precisely the situation we may be in right now with exoplanets. Not wrong through negligence. Incomplete through the honest limitation of where our technology currently stands. Einstein himself spent years defending a cosmological constant he had introduced into his field equations, a term he later described as his greatest mistake. The history of science is not a sequence of correct answers. It is a sequence of answers that were good enough until the next instrument arrived and showed us what we had been missing. Pull back from the data for a moment, set aside the mass thresholds and the spectroscopic readings and the orbital mechanics. There is something quietly profound sitting at the center of this debate that does not appear in any academic paper. Kelt 9b is losing 100,000 tons of its atmosphere every single second. It has been doing this for millions of years. It is being slowly erased by the star it orbits, stripped down layer by layer, and it has no mechanism to stop that process. By any measure, it is dying. And yet, it is still there, still completing its orbit every 1.6 Earth days, still present, still measurable, still real. The atoms currently leaving Kelt 9b's atmosphere, the hydrogen being pulled away and consumed by its star, were forged in the core of a previous generation of stars that died long before our sun existed. Those same stellar cores produced the carbon, the oxygen, the iron that eventually found their way into you. At the atomic level, the difference between you and a failed star is a question of arrangement and proportion, nothing more. So, when we ask whether an object at the boundary between planet and star represents success or failure, we are perhaps asking the wrong question entirely. Kelt 9b has existed for longer than complex life has existed on Earth. It will likely continue existing long after we are gone. Whatever it is, it has outlasted most definitions of success we could apply to it. The universe does not appear to grade on that curve. The honest answer to the question at the center of this video does not exist yet, but the tools that may produce that answer are either already operating or are close enough to their launch dates that we can speak about them concretely. The James Webb Space Telescope has been collecting data since late 2022, and its contributions to this specific debate have already been significant. Its ability to analyze the atmospheric composition of exoplanets and brown dwarfs with a level of precision that no previous instrument could achieve is gradually giving scientists something they have never had before: large enough sample of atmospheric data to look for statistical patterns across the full population of objects in the planetary and substellar mass range. What Webb is beginning to reveal is that atmospheric chemistry does not sort itself neatly along the lines our classification systems predict. Objects on the same side of the 13 Jupiter mass boundary sometimes look more similar to objects on the opposite side than to their supposed category neighbors. That is not a conclusion, it is an early signal. But early signals in astronomy have a history of becoming paradigm shifts given enough time and follow-up observation. The Nancy Grace Roman Space Telescope, currently scheduled for launch no later than 2027, will extend this work in a different direction. Its field of view is approximately 100 times wider than that of the Hubble Space Telescope, which means it will be capable of monitoring enormous sections of the sky simultaneously for gravitational microlensing events. This is the detection method best suited for finding isolated brown dwarfs and rogue planetary mass objects, the ones with no star to orbit, drifting through the space between star systems. Current estimates suggest these objects may exist in numbers comparable to or exceeding the number of stars in the galaxy. Roman should give us our first statistically meaningful census of that population. Then there is the European Space Agency's Ariel mission, currently scheduled for launch in 2029. Ariel is specifically designed to conduct atmospheric surveys of approximately 1,000 known exoplanets, a sample size large enough to move this conversation from individual case studies into genuine population science. For the first time, we may be able to draw a continuous map of how atmospheric properties change across the full spectrum, from small rocky worlds to massive objects at the boundary of stellar classification. Here is the prediction worth making carefully, and explicitly, as a prediction rather than a certainty. These instruments will likely not resolve the classification debate cleanly. What they will almost certainly do is provide enough data to demonstrate that the debate itself was framed incorrectly from the beginning, that the question is not where the line between planet and failed star should be drawn, but whether a line in that location reflects anything real about how the universe organizes matter. That would not be a failure of science. That would be science working exactly as it is supposed to. The universe did not invent the word planet. We did. It did not draw a line at 13 Jupiter masses and decide that everything below that line deserved one category and everything above it deserved another. We drew that line with the best tools and the best reasoning available to us at the time, because human understanding requires boundaries in order to function. We build fences around concepts the same way we build fences around property. Not because the land itself demands it, but because we need to know where we are standing. But the objects we have looked at today do not respect those fences. They sit on the boundary lines, or they exist in ways that make the boundary lines seem almost beside the point. A planet hotter than a star, a world that survived the death of its sun, an object that formed like a star but lives like a planet, a brown dwarf with the atmospheric chemistry of a gas giant. Perhaps the most accurate thing we can say is this: the universe operates on a continuous spectrum, and we are pattern recognition creatures trying to impose discrete categories onto that spectrum. We will keep adjusting our categories as the data demands. That is not a weakness. That is the entire mechanism by which science moves forward. These objects at the edge of our classification systems are not anomalies to be explained away. They are invitations to think more carefully. If that kind of thinking is what brought you here today, this channel exists for exactly that reason. Leave your thoughts in the comments below, particularly if you think the formation-based or property-based classification argument is more convincing, and why. And if there is a specific exoplanet or astronomical boundary question you want explored next, say so. The next direction this channel takes is genuinely shaped by those conversations.